Myself, Dr. Vatsa, and so I'm going to share my screen, and here it is. And I'm glad it is Friday afternoon, and for Friday afternoon, I always feel like a heaven. Do you know why? Because Friday sees more smile than any other work day. So, and particularly it's Friday evening, so everybody is happy. So that's like it's a heaven, and that's a great thing. And second reason I like Friday, the Friday is the second most important F word in my life. First is food, and this related with the food security. It means this algorithm has been tested on food security kinds of stuff. So that's why I like Friday. Okay, let's start. So this is the one of the standardization methods. I call it SDFS. I'll come to it in detail in a moment. And it has been tested, it has been found under the one of the experiments. Everybody is able to hear my voice, right? And slides as well. Yes, I want to show. Everybody is able to hear my voice, right?
What?
Am I audible?
I don't understood.
Oh, yeah, we're able to hear. Yeah, okay, yeah, we can hear you.
It's clear.
Okay, thank you very much. So this is the one of the we found this method in the one of the experiment, and the goal was that experiment to improve the rate of crop productivity. So it was the matter of food security, and the basic hypothesis was how we are going to increase food product in a corn plant. Here the species is corn basically, and the experiment name was abiotic stress growth condition response on a distinct maize embryo line. So embryo line is just like a genetic characteristics of the maize plant, and they were treated with the nitrogen and water mixture, and they conducted this experiment in the greenhouse. And through those experiments, I was trying to find the group of similar phenotype, and the basic constraint was how we are gonna map this group of phenotype, similar phenotype with the genomic sequences or genetic symbols. And in order to increase the food productivity, that is one of the phenotypes that called yield. So that is the experiment, and that was created. And here is the information about the experiment. So this species is maize. It was planted in greenhouse. There was 90 embryo line. So embryo line is just like genetic characteristics. Like my genetic characteristics is my mother and father. Similarly, every maize also has their genetic characteristics. There is no mutant have been used, and the nine growth conditions have been used, and that is the nitrogen and water mixture. So urea and water mixture. And we measured 3 phenotypes, that is difference in plant height, difference in canopy spread, and difference in stem diameter. And that is the manual measurement. And there were 8 dimensions originally. And once we found some characteristics of the data, then we identified actually many plants were died once we treated with the nitrogen and water. And similarly, many plants shrank once we treated with the nitrogen and water. So once plant died, we have missing our data value. So, and very sparse value is there because many plants died and many plants survived. So I'll come to the actual figure, how many plants were there and how many survived and how many shrunk. So this is the maize phenotype. First of all, I would like to introduce the phenotype. Phenotype is nothing but it is an observable and measurable trait. Like you could measure my phenotype, my height is short and too fat, and my look is ugly. These are my phenotypes. Similarly, plants, we have measured height, canopy spread, and stem diameter. And it has been collected. These 3 phenotypes, plant height, canopy spread, and stem diameter have been selected under the 9 conditions. And this is the 9 conditions that we have. So we treated those plants through the 9 treatments. And this is the water axis, and this is the urea axis. And these water and urea corresponding composition is over here, like the T1 is the treatment 1, T2 is the treatment 2, and similarly T9. So we have planted 4 plants under each treatment and 8 plants under the treatment 5. and it has been designed by the geneticists, so I can't say anything. My background is from the computer science. So there are about 40 plants for each emerald land. So 8 multiplied by 432 plus 8, 40 plants. So 40 plants for each emerald land, and we have 90 different emerald lands. It means there are 3,600 total plants. We treated them with the treatment, and we collected their data, that is a canopy spread, a stem diameter, and height. Once we collected those data, we found many characteristics. First of all, that is the multidimensional data. Now there are 3 dimensions over here. And we have observed from those data sets, many plants, since many plants died, many plant height shrunk due to the treatment of ammonia and water. So at that point, many values are 0, many values are negative, and many values are positive. In overall, I'll show you the distribution. We found our data is sparse. So there was many big challenges while we are trying to find a group of similar phenotype, and for the computer scientists, it is just a cluster analysis. Since data sample was small, because we have 4 plants and 2 plant died, and we have only 2 samples. Similarly, we have 5 plants and the 3 plant died, we have 2 samples, sometimes 1 sample. So that was the basic challenge. So we can't calculate the statistical parameter value because the data sample size is very small. I can't consider the mean value, median value, or other statistical parameters. So that's why we call it non-parametric in nature. This data set has non-parametric in nature due to the sparse characteristics. So that's why we are going to apply a non-parametric clustering algorithm in order to find group of similar phenotypes. So as in the data scientist, I would say, since these parameters were observed from same objects, then it's a paired characteristic. So we measured, that is before plant height and after plant height, and then we got the difference in plant height, difference in canopy spread, and difference in the stem diameter. So that is so we reduced from the 6 dimensions to the 3 dimensions. So that is the dimension reduction kind of a stuff. And we got help because these parameters were observed from the same object. Next problem is how we are going to compare these data points, because the range of plant height and range of canopy spread and range of a stem diameter was different. So in order to take any analysis or apply any analysis on the data set, we'll have to rescale them. And while we adopting the rescaling, we also considered we should not change characteristics of the data set. So in order to do that, we apply min-max linear transformation, and this is the mathematical formula we have applied, and we rescaled our whole data into between the 0 and 1. Thereafter, there was another approach in order to find the clustering, that is the standardization. And the basic purpose of the standardization was how we are going to put whole data set in the same variance, because once you have same variance of the data set, at that point you are going to allocate the data point to the respective cluster. So cluster allocation will be simple if you have the same variance. So in order to do that, we can't calculate the statistical parameters like the mean, median, or the standard deviation or variance or any other statistical parameter, since our data sample is very, very small and data sample is sparse. So at that point, our existing standardization method was not supposed to work, and though I have tested this method. So first of all, I'm going to talk about the existing standardization method. So existing standardization method, we could be represented like this mathematical equation. Since we have very less time, so I can't go through the details of this equation, but the whole 17 existing methods could be represented as this one. And the basic important thing is this formula using some statistical value like the gamma. It is the some statistical parameters like the mean, sample variance, weight, and according to the different standardization method, existing standardization method, these things are required, these parameters are required, and we can't calculate on our data set because our data is sparse and have very small sample size. So that is the basic reason behind proposing the new standardization method, and we call it SDFS, Standardization for Distribution Free Statistics. And this is the mathematical formula that standardization methods that I have proposed. And thereafter, in order to verify this, really this standardization methods work in order to find our group of similar phenotypes. So what we are going to do, first of all, this is the results of the data set. We have tested for the 18 methods, including my method. So here I am going to show you only 3 methods results, because the most of the results, they either belong into this group or this group or this group. So that's why I categorized the whole 18 methods into the 3 groups, and I included the results of this one. So this is the distribution of the original data set, and you could here see this is the 0 value, and it's clearly so this is the difference in height, canopy spread, and stem diameter, a ton of 0. And we found about 60%, about 55 to 60% of the sparsity in the data set among 3 dimensions. Thereafter, we applied all 17 methods, including mine, that is 18 methods. And so first of all, this is the standardized distribution. So this is the mid-range, this is the ABW, and this is my method. Again, everyone predicted the same sparsity of the data set. Someone has 3 forks, someone has 2 forks, and similarly, I also have 2 forks. Then we applied MODECLUS clustering algorithm. This clustering algorithm is for the non-parametric clustering. In this method, the beauty is this, in this method, they are not using any distance metric. It means we are not going to use any distance metric like the Euclidean distance, city look distance, or anything. So that's why this clustering method sounds good to me for the non-parametric data. And it was clustered. It means they are going to take a radius of R, and this is the theta threshold value of, so they're doing R radius volume or a sphere, and they're calculating how many data points belongs to inside the circle. They count it, and per unit volume, they're calculating the density of the data set. But this algorithm has 2 challenges. First of all, how we are going to consider R value and theta value. So in order to do that, we have tested this algorithm. This plot is very nice. We have considered on the y-axis radius and density threshold on the x-axis, and thereafter we trying to introduce the classified points and number of class with a classified point. It means the biggest circle shows 100% classification. It means all data points have been allocated to some cluster. So here we found if we have our density threshold value between 3.5 from the 0 to 3.5, and the radius value between 0.2 to 5 up to 5, then we could get all classification 100%, and the number of cluster vary according to that. And so that's why we have to consider, take the value of R and theta between this area, right? Now we applied our mode cluster algorithm on all 18 methods, and what we found, the mid range, it's showing this is the cluster one. It's very sparse cluster, and we were looking for the natural cluster. Natural cluster, it means the cluster must be the arbitrary state, and they may be overlapped to each other. And here the color of the data point shows the number of clusters. So mid range shows about more than 100 clusters. I'll show you the actual figure in the next slide. And AVW shows the very few number of clusters, but they just overwhelm to each other. It means overlap to each other. So it doesn't sound good to us. And thereafter, this is the SDFC. SDFC is our proposed algorithm. We found only 6 clusters, and here the clusters are very organized and they are overlapping to each other. And so that is looks like a natural cluster to us, and it was acceptable to geneticists. So this is the actual figure that we got. And here we got SDFS only 6 cluster, 100% classification. ABW also got the 19 cluster and 100% classification, but geneticists observed their experiences, there was no 19 cluster available in an actual experiment. 6 was available, and that was acceptable for the geneticists. Mid range showing the hundreds of the cluster and 59. All other clustering standardization methods I applied, and these are the clustering. number of clusters, and these are the classification one. So here I could say SDFS method is better in comparison to all other existing 17 methods. And thereafter, we also want to test a scalability feature of this method, and then we generated the synthetic data set using the Python NumPy function that is very popular in the Python, and we generated those data sets of the different sample size. And we made sure these distribution must belongs to the similar distribution of the original or raw data set that we got in our experiment. And it looks like similar, it's a sparse, and the sample size is 3,000, 6,000, 7,000, and 10,000. And since it's a non-parametric technique, so we will have to provide the accurate scalability value in what kind of the data samples this standardization method would be the valid. So that's the reason scalability is the one of the biggest stuff in this method. And we applied the MODECLUS methods and SDFS method. Here we found whenever we have data sample 3,000 and 10,000 exactly, at that point only 2 clusters identified, here also 2 clusters identified, and that seems appealing to us. Though one sample size is 6,000 and 7,000, it's identified natural clusters and the sufficient number of clusters we identified over here. So what we got for the conclusion, once we have the data sample more than 3,000 and less than 10,000, at that point, this standardization method would be the wonderful method for the non-parametric analysis where we have a sparsity in the data set. So this is the limitations that I discussed a moment ago. So it's good for the low dimensional phenotype. Here it is a 3 dimensions, so up to 3 and 4 dimension, it's good. And it is very good for the sparse and small data set. I gave the scalability range. And this method could be extended further for the multi-regression and factor analysis or the classification method. I have already expanded for the high dimensional data, and I propose another clustering algorithm that is known as the DynaDAX. That will publish very soon in another paper. So this is the summary about the SDFS method. It's the non-parametric method, and it read off outliers automatically because this standardization methods have that kind of the beauty, and it's applicable for the sparse and the boundaries or during the clustering method, and it will be wonderful application for the farmers, geneticists, agronomists, and plant scientists because they do have these kind of the data set in almost every experiment, not every experiment. Thank you, and I thanks to Dr. Ann for sharing the data set and Dr. Chan for advising. Tony for the advising, and thank you. If you have a question, I would be glad to answer your question. Thank you.